So let's start again from part 2. So my name is Yasushi Sakurai of Kumamoto University, Japan. And thank you for coming, thank you for attending. So part 2 is, title of part 2 is nonlinear modeling and forecasting. So this is the roadmap, problem, fundamental, and applications. So let me introduce why nonlinear mining is useful. So example is a logistic parabola. This parabola expressed with this equation. So and we can synthetically generate data by using this equation. And this is logistic map. And this is delay coordinate. And this is logistic map. So problem is, so given time series data, and we want to predict the future data, like this. So we want to forecast the future data. So we can consider the several solutions. So solution number one is linear equation, like AR. And Arima, or which is they are presented in part 1. So if we try to fit this data, so AR it doesn't work for this data because AR assumes a linear assumption. So it is hard to predict the nonlinear phenomena. So then we have to think about another solution. So solution number 2 is we use delay coordinate embedding and also use k-nearest neighbor search. This is also a very simple idea. So now we have our time series data and also we create a delay coordinate. So this horizontal axis is xt minus 1, and the vertical axis shows xt. So for every time tick, so we create a plot of and map them on this delay coordinate for every element of time series data. And now we have a new point. Then we use a k-nearest neighbor search with we pick up 4 nearest neighbors like this, and we compare with project on xt. So, and we interpret these 4 points and also to get a final predictions. So this is a very simple idea. So occasionally frequently it works. So for example, logistic parabola, for logistic parabola, so this idea works well. And also for Lorentz, it works well. And laser, it also works well. So yes, so and this is nonlinear forecasting. So it doesn't assume the linear assumptions. So yes, it can work, but sometimes it is hard to interpret. So that's why we need another solution. So in this case, we call it black box mining. It is because we don't know the equations. But if we know the equations, so we can use it for forecasting, for modeling. So we call it gray box mining. Okay. So there are many nonlinear equations in for natural and social phenomena. For example, population growth, or competition, or information diffusion in social networks, and also epidemics and convection. Okay, so let me introduce them. Okay. So yes, let's focus on population growth. So it is a logistic function. We can call it is also called Bauhaus model or sigmoid or Bass model. So this species consume the food resources and to increase the population. So logistic function shows the population expansion with limited resources, like this. T equals 0, T equals 1, T equals 2. It is growing. They're growing. So population expansion with limited resources is described with this equation. And P shows the population size, and like this. So this point is the initial conditions, and R is growth rate, and K is carrying capacity, which means available resources. Because yes, so we have a limit. Another equation is Rotka-Volterra. So it is called prey-predator model. So prey and predators. H shows the count of prey, and P shows count of predators. So it is this phenomenon also described with these equations. So this is an example of Rotka-Volterra. So now consider the jungle. So there are squirrel monkeys and spider monkeys. They share the food. They share the fruit. And the capybara, in this case, they don't share the food resources. So in this case, spider monkeys and squirrel monkeys has competition. So to get the fruit. So Rotka-Volterra equation shows a competition between multiple species, like this. And in this case, A shows the interaction coefficient between I and J. So, or we can say that the effect rate of species J on I. So, if number of species for squirrel monkey is increasing, so number of spider monkey is decreasing because they have a competition, right? So it is hard to get food resources for spider monkeys. So like this. So the effect rate of species J on I. So spider monkeys and squirrel monkeys. Okay. And there another. So we can call it biological interaction, or no effect, beneficial, something like that. And another nonlinear equation is epidemics. For example, suspected infected model, SI model. It is a very famous model for epidemics. And S is healthy and I is infected. So for example, in the figure, everyone is healthy. Okay? And if this guy is infected, so which leads to infection, which leads to propagation with the beta infection rate. So, and this we use this equation for to estimate the model parameters. And beta is the infection strength, and then the population size. Okay. And this is a logistic function and SI model. And its variant is suspected infected recovered model, SIR model. So SIR, and also beta is the infection rate, and gamma is the recovery rate. So example again. So now again, everyone is healthy, and he is infected. So which again leads to propagation. Okay? But the first guy is recovered. And so which means, it means no more infections. And then everyone is recovered. Okay? So everyone is recovered or healthy. So let me speak in detail, but so in this case, everyone is recovered or everyone is healthy. So, another epidemic models, SIS or SIRS, and so on. And we can also consider information diffusion in social networks. In this case, so nonlinear model is very useful to estimate the property of information diffusion in social networks. So we can consider how news or rumors spread in social media. So as an example of news spread in social media, so meme tracker, which is proposed by KDD 2009, which is meme tracker is short phrases sourced from US politics in 2008. This is a number mentioned in blog. And the example is you can put lipstick on the pig. So, and another example, yes, we can. So for both cases, we can see the three parts of the situation. So first one is breaking news. Next one is news spread, and also decay, because people forget the news or they lose interest in such a short phrases or news. And another example is Twitter, Assange or Steve Jobs. So these figures shows number of hashtags per hour, and also Google Trends, which is number of queries per week for Google service, and Tsunami or Harry Potter. So question is that how many patterns are there in social media? How many patterns of news spread in social media are there? So Crane at all says there are 4 classes, or Young at all says there are 6 classes. So if we focus on 2 patterns, so they look different at first. For example, Tsunami has a sudden peaks and rapid relaxation. And Harry Potter movie, symmetric relaxation. Okay. So they look different, but we can estimate, so we can fit with all of them with only single model. So we want to introduce a method, so which is published in KDD 2012. So rise and fall patterns of information diffusion and modern implications. So our model, we call it spike M, and captures 3 properties of real spike. So first property is we can see the periodicities, okay, and avoid infinity, and power of fall. Okay. So spike M captures the behavior of real spike using few parameters. Okay. So let me give you an example. So everyone is uninformed rumors. Everyone don't know such a rumor or news. And the external shock happened. So it leads to information propagation. So with beta. Beta is strength of infection, or quality of news, or strength of news. So, and also we introduced decay function. So how effective a blog post is. And we use a power of 4. So this is a base equation. But the point is that we also use a periodicity because bloggers change their activity over time. So sleeping time and date time or something like that. And spiking consists of 7 parameters. So to run the parameters, we use a Levin-Marquardt fitting. So Levin-Marquardt fitting is very easy to use, so very useful and easy to use. So to fit the model, okay, and our model consists of 2 parts: experimental right and also power of 4, like this. So there are 6 classes, but our spike fits very well for everything. And also meme tracker, experiment result of a meme tracker, and also hashtag data. So, and Google Trend data. Sorry. And so give the, for example, we can also do the tail part forecast. Given a first part of spike, we can forecast the tail part. Okay. So this is now first part is given, so we can forecast tail part. So in this case, AR doesn't fit very well. AR does not work well for forecasting. Okay. And also, we can also do the fatigue forecasting, which is one application of this model. So we can forecast not only tail part, but also right part. So necessary. So we need some information to forecast the right part. First one is first spike. So this example. So this example is a Harry Potter movie. So Google data of keyword Harry Potter. So and for example, this movie. Harry Potter and the Half-Blood Prince, which was released in 2009, and we learned this spike and estimate the model parameters. Then we also need this date of 2 next movies, and also access volume before the release date, so we can forecast the right part for 2 next movies. Okay. And also, it is also useful for outlier detection by using a tail part. Okay. So let me skip it. So we are running out of time. So another example is, another application is online competition. Okay. So online competition in social networks. So in YouTube and Twitter and Facebook. So there are many, we can see the many competition. So how can we describe the virtual competition? So there are many solutions. First one, Parakesh et al. Presented in 2012. So iPhone and Android has a competition. And also Blu-ray and HD DVD also has competition. So if we assume that they are virus, so what happens when 2 viruses compete? For example, green one, virus number 1, and red one, virus number 2. So if virus number 1 is stronger than virus number 2, what happens to the next? So answer is winner takes it all. So virus number 1 takes everything, and virus number 2 dying out. Okay. So they use their method is based on SIS mode, and they modify such a model, full-life model. So let me skip detail, but this is also, they are also example of their experimental result. Okay. And another one is Wave at the Jungle, which is we published in 2015. So now let's consider the Google search volume for 4 keywords: Xbox and PlayStation and Wii and Android, and these are 4 sequences of Google search volume or number of retrievers for Google service. So we want to capture the trend, and we want to estimate the exponential growth and interaction between keywords, and also seasonality, fully automatically. So problem is that given co-even online activities, so we want to find a compact distribution wave X, okay, which include nonlinear evolution and also interaction or competition, and also seasonality. Okay. For example, this is a sequence of Xbox and PlayStation and Wii and Android. So probably you are not familiar with the game console, but let me explain. So Xbox and PlayStation is a game console for heavy game users, okay, and Wii is for light users. So if we use the nonlinear equation of competitions, we can automatically find such a we can automatically find extract such information about interaction networks. So, for example, Xbox and PlayStation has a competition because they are game console for heavy users. So, and so this Xbox, PlayStation has consumed much more resources. So, and also Wii is a light user game. So, and light users are also interested in mobile game. So that's why Wii and Android has a competition. Okay. So the circle shows the keyword for Google Trend. So, and it shows the competition between Wii and Android. And the arrow shows the strength of interaction. Okay. And we can also find the seasonal component. So for 4 keywords, game console. So this one shows the E3, Electronic Entertainment Expo in June. And also summer vacation, because for example, students are really interested in games, so that's why summer vacation, the activity of game console increasing. Okay, and the next one is Black Friday and also Christmas. So main idea is that we want to describe the evolution of X. Okay, so in jungle, this one. So squirrel monkey and spider monkey has a competition, and capybara they have the glasses, and their competition. It is an ecosystem. So we believe that the same happened to the web. Okay, we can call it the ecosystem on the web. Okay, Xbox and PlayStation has a competition, and Wii and Android also have a competition. So this is analogy of this method. So biological species consume food resources to increase the population. Okay, the same happens to the web. Online activities or keywords consume the user resources. So user resources is for example, user interest or user's time or user's money. So keyword consume the user resources to to increase the popularity. And also climate or season affects the activity of the biological species. The same happens to the wave. So annual event like Christmas, or Black Friday affect the online activities. Okay. So we estimate the model which include nonlinear evolution and interaction and seasonality. And for nonlinear evolution, so population size increase over time. And also, which is described with this equation. Again, P is the initial conditions, and growth R the growth rate, and K is the carrying capacities. So available user resources instead of available food resources. And competition, and they share the food resources, and also Andrew and we share the user resources, like this. And A is again interaction coefficient, so between I and J, and also seasonality. And so user change behavior according to the seasonal events like Christmas and Black Friday or Happy New Year. So let me skip it. So we can estimate the seasonal patterns. So by using ICA, ICA is presented in part 1. So for ICA, like this. So B is a seasonality matrix, which means a basis or component. So or eigenvector or something like that. So B is a seasonal matrix. So and also W is a partition weight matrix. So and in this example, K2, Q2 is a number of seasonal pattern is 2. So we compute let me skip in detail, but we compute the seasonal pattern by using ICA. Okay, and also we have to appropriate number or optimal number of. We can use it. You can use MDL to estimate the appropriate number of seasonal patterns automatically. So let me skip in detail algorithm. But yes, now again video came. So we can see the interaction between keywords and seasonality. And another example, programming language C, R, MATLAB. So if we use our method, so we can see the interaction between C and R. But but MATLAB does not have any competition. And also we can extract the seasonal pattern like this. So during the summer, activity of program language is very decreasing because students forget about the programming. So that's why the activity is very low during the summer. And the same happens at Christmas and New Year and March breaks. Okay, and also for example of social media. So Tumblr, Facebook, LinkedIn. In this, if we analyze such as time series data, we can extract the information about the interaction. So Tumblr and Facebook has an interaction or competition, but LinkedIn does not have any competition in this case. Okay, and also operator company called JCPenney and Nordstrom for 21. So in this case, JCPenney and Forever 21, they have a competition. And Kohl's and Nordstrom has a competition. And all of them share the seasonal event, so seasonal patterns, so which include the back to school and also Black Friday, yes. So another example, okay. And by using such a model, we can forecast future data, okay. So given we train these sequences, and we can forecast the rest of them, okay. And which is this method, so nonlinear equation. So this method uses nonlinear equation, which is better than the linear modeling, okay? Like this. And yeah, sorry. So everything is done, but let me explain extension. So nonlinear modeling for data stream. So there are many big time series data stream in for social or natural phenomena like motion sensors or online activity like Google Trends. So we want to forecast future events. So which is published in KDD 2016. So problem that given coeval event stream, so we want to forecast n step ahead for future event at any point of time. So in this case, we focus on real-time forecasting. We believe that which is very useful for IoT. So for example, self-driving car or smart factories or something like that. So what is the ideal solution for real-time forecasting? So it should forecast it should do long-term forecasting, okay? And also it should be continuous, okay? And also it should be based on the nonlinear modeling. And also ideal solution should be adaptive. So what is adaptive? So if we consider the self-driving car, to achieve self-driving car, we have to forecast the future. For example, 5 seconds later or 10 seconds later. So, but it should be adaptive because if another vehicle suddenly move to the same lane in front of us, so we have to care about such a behavior. So in such case, specifically, we have to change the model to predict the future. So that's why for real-time forecasting, so ideal solution should be adaptive. Okay. So mainly idea consists of this latent nonlinear dynamics and also regime shifting stream and nested structure. First one, we should use a nonlinear modeling. So because we use many models to express various patterns, like for example, motion capture data. Various patterns include walking and stretching and another stretching, and we need a 3 model to express such a data. Okay. Next idea is that we have to change pattern in stream, change of pattern in stream. So at first he's walking, and which is expressed as a model of regime number 1. And then the second motion, stretching, we also need another model. And this is we need a model change. Okay. So in the research area of biology, so regime shift is a very hot topic. So for research, so yes, we can call it regime shift in natural systems. So in this case, regime shift from woodland to grassland. Okay. So for example, the same it happened. For example, forest fire or big fire. So this shift is an abrupt change in the structure of complex system. So, for regime shift from woodland, grassland by forest fire. So another example is regime shift between core and macroalgae and desert and vegetation. And yes, so the left figure shows the regime shift in natural phenomena, and the same, we believe that the same happened to the motion sensor or IoT. Okay. So regime shift in stream. So third idea is nested structure. So for example, if we forecast the chicken dance, we use two types of model. One is for long-term forecasting. Another one is for short-term forecasting. Okay. Or we can combine these models to for better forecasting. Okay. And the problem definition, we focus on current window of original event, and we choose the model, best model among the many models, and do the forecasting. Okay. And this is, so let me explain by using this figures. So this is the structure or architecture of our system, forecasting system, and we receive the data stream X, and which consists of many patterns like this, like this, like this. So we create the many models according to the patterns. Okay. So we estimate the model for each different pattern, and estimate the parameter and store them in the model database. Okay. And okay. At first, we extract the current window, and for example, this pattern, this subsequence is very similar to this model. Okay. This one there. So to forecast the future data, we use this model because this model fits current window very well. Okay, that's why we use this model for forecasting. Okay, so step number 2 is to find the optimal regime or best one. Okay, and unfortunately, if we don't have a good model for forecasting, so we have to estimate a new model and store it in the model database. Okay, and also use it for forecasting. And estimate the future event by using selected models, and provide the forecast future data. Okay. So let me show you a demo. This figure shows the original sequence, which is a motion capture data, which include walking and which includes walking and stretching or some various stretching. Okay, and bottom one is current windows. Okay. Dotted line is the original sequence, and the curved line, red line or blue line, so green line. So they are models. If curved line and dotted line fit very well, so we can say that a model is good for forecasting. And middle one is forecasting result. So we focus on current window, arrival event, and select the good model for forecasting, and we use it for forecasting. And this is 100 step ahead forecasting, and we mapped this to the middle of the figures. So, okay. So at first, we don't have any model in the model database. So now he's walking, so we estimate the walking model and store it in the model database and use it for forecasting. Okay, and if he changes the motion, so we estimate another model and store it in the model database and use it for forecasting. And he showed the same motion. So in this case, we use the previous or old model for forecasting because his motion is the same. Okay. Okay, 3, 2, 1, 0. So now he's walking. So algorithm use the walking motion model for forecasting. And he shows the different motion. So algorithm estimates a new model and use it for forecasting. Oh, sorry, this is a different motion. So estimate the model and use it for forecasting. Okay. And yes, algorithm said that, I know this motion. So use this old model for forecasting. Okay. Oh, this motion is also well known. So use it old model. He used the old model for forecasting. And now he's walking. So algorithm used the old walking motion for forecasting. So that's why. So it's okay. This is the result. So if we use the statistical model, so it is hard to do the forecasting. So because he changed a lot, so we have to change the model for forecasting in real time. Okay, so many companies are interested in many IoT companies are interested in this method. So because the accuracy is very good, okay, by using many models, okay. And also this is another experimental result. So mocap and chicken dance. So this is experimental result of Google Trends. So Google Trends, this one is search volume for 4 keywords: Netflix, Hulu, YouTube, and Amazon. This is the original data. This is a result of forecasting, 3 months ahead forecasting. We can say that this algorithm says that he knows which is a hot topic 3 months later. Okay, and also this is another experimental result, beer keyword. So yes, the time series data it's very complicated, but algorithm work well for forecasting. Okay. And another result of Google Trend, and also this is air pressure and temperature. And forecasting, it is a result of 3 months ahead forecasting. And also, this is another experimental result, exchange rate of yen and dollar. So this is the original data. And bottom one is 6 weeks ahead forecasting. Okay. And right here shows the price of gold and platinum. So this is the original sequence, and this is 3 months ahead forecasting. So it works well for forecasting. And this is a fitting result of our method. And the others, ARIMA or T-bar is a state-of-art method in statistics. And so regime can identically regime shift dynamics in real time. So in this case, it is hard to predict the future data. So we want to solve it with algorithm. So an adaptive algorithm to solve such a problem, difficult problem. And this is a forecasting error. This is good. And also, yes, scalability is also great. And let me skip it. So, yes, that's it. So for part 2, yes, okay. As a conclusion, so we introduced nonlinear modeling. So, and the concept and the fundamentals and applications. So, epidemics, information diffusion, and online competition. And so there are references, and you can download from our website. You can download this file from our website. Okay. Okay, let's move to part 3. Okay, sorry. Tensor analysis. Extension of time series data, tensor analysis. Okay. So this is the outline, tensor decomposition, and also tensor analysis is useful for complex time-stamped events, and also a new challenge. Nonlinear tensor analysis. So yes, first let me introduce motivation. So example metrics like graph, social networks. So John connect to Peter or Mary and Nick. So it is a graph structure. So we can describe it with metrics. And another example is a crowd of n-dimensional points. For example, they are patients and cholesterol number and blood number and age and something like that. And another example is a market basket for association rule. So John has bought a milk 13 times, bread 11 times, chocolate 22 times, and wine 55. So another example is document and term. So paper number 1 has a term data 13 times, and also term mining 11 times, classification 22 times, tree 55. It's similar, but another example is author and term. John published a book on paper which includes term data 30 times, and mining 11 times, classification tree 22 and 55. Another example is sense ID and time ticks. So now we have a sense node of temperature. So temperature number 1 at time t equal 1 is 13, t equal at t equal 2, 5, something like that. And also humidity and pressure and so on. And so tensor is very useful, and tensor is any dimensional generation of matrix. For example, now in the KDD this year, author John published a paper which includes a term network 30 times, and search, keyword search contain search 11 times and graph 22 times and so on. And so this is a matrix of KDD this year, and we also have a matrix of KDD 16 and matrix of KDD 2015. Okay. So this is a tensor. This is an n-dimensional generalization of matrix. Okay. And we can also say mode. This is, for example, this is an example of third mode tensor. So first mode is term, network, search, graph, mining. And also second mode is author, Joe and Peter, Mary, and Nick. And third mode is most number 3 is the conference, KDT this year, last year, and so on. So tensor is very useful. Tensor analysis is very useful. For example, social networks. So we want to, occasionally we want to monitor networks and community structures over time. So for example, keyword, also keyword matrix, and also property is changing over time from the 1990 to 2004. For example, this author. Yes, this is a focus on database. Yes, and yes, and we also have the database and data mining and so on. This is it changes over time. Okay, and we can order the importance of web pages by using Kleinberg algorithm, heat, and PageRank, and so on. And another example is a timestamp event. For example, web click. So this table shows a data set of web click, which include time and URL and user, which this record shows that Smith accessed cn.com on August 1st, 12 p.m. So we can create a third order tensor. Okay, like this. This direction shows the time, and this direction shows the users, and this direction is the URL. So, and one element in the tensor X. So this element X shows Smith access cn.com at 10 p.m. on August 1st, 21 times. Okay, and this is the example of third order tensor, where M order tensor and where M is 3. Okay. And instead of using individual sequence mining, we should use a tensor analysis in this case. So for individual sequence mining, we create a set of U times V sequence of length n, and we apply the mining algorithm to each sequence. So, for example, AR or common feeder and so on. Okay. But in this case, we occasionally lose the information or useful information. So instead of using individual sequence mining, we can use a multi-aspect time series analysis, like tensor analysis. So in this case, we can extract the information about topic, like business and news and media and so on. So we can do the good analysis and also good forecasting. Okay? And basic approaches. So yes, SVD, so which is presented in part 1, like this, and we can also describe it as like this. So feature number 1, feature number 2, and so on. Okay, like topic. Okay. And the goal is that we want to extend to the more than 3 modes like this, which is very similar to SVD case. Okay? SVD is for 2 modes, and tensor is for in this case 3 modes. Okay? And let me introduce that. 2 major types of tensor decomposition, Parafak and Tucker. And we can solve it with, by using ALS, alternating least squares. So this is an example of Tucker decomposition. So example, X is a matrix of author times keyword times conference. Sorry. So A is a matrix of author times author group, and B is a matrix of keyword and keyword groups, and C is a matrix of conference and conference group, and G shows how groups relate to each other. Okay, so let me explain with this example, 2D case. So 3D case is hard to explain, hard to visualize. So let me use a 2D case for clustering. Okay. So let's consider the matrix of term and document. Okay, and which include medical documents and also on the CS computer science document, and also medical terms and computer science terms and common terms. Okay. So if we use a Tucker decomposition, we can get such a three matrices. First one is a matrix of term and term groups, like medical term and CS term and common terms. And also, second one is a matrix of term and term groups times document groups. So it shows the relationship between term groups and document groups. Okay, and third one shows a matrix of document times document groups. Document group means a medical document and also a CS document, like this. Okay. So for Tucker decomposition. So let me start this. So Tucker decomposition. So and G is not untitled, and ABC generally assumed to be orthogonal. Okay. And another decomposition, paragraph decomposition. In this case, core is diagonal. Core is diagonal, and column of ABC are not orthogonal. So, and if R is minimal, so R is called rank of the tensor. So this is a difference in Tucker paragraph. So Tucker core G may be dense, and ABC generally orthogonal. And on the other hand, paragraph no core, super diagonal core, and ABC has a linearly dependent column and linearly. And so we can use two main tools, paragraph and Tucker, and we can solve them by using alternating list squares and the toolbox. So they are very useful toolbox, especially from Professor Porter. And I want to show the extension of the tensor analysis for complex timestamp events, which is published in Carnegie in 2012. Now we have the table of webclick events, which includes the timestamp, URL, user, device. So first column shows a record where Smith accessed cn.com on August 1st, 2012 from the iPhone. And so we want to capture the trend. So for example, cn.com and cn.com are related to news topic, and user.com is related to media topic. And we want to group URLs, users, and forecast future events, like how many clicks from Smith to know, or how many clicks to cn.com over next 7 days. So it is very difficult problem, but this is one approach for this problem. So we use the webclick. So this here shows the original access count of each URL, money site and blog site. So each column shows different users. Okay? And if we forecast future data, in this case, it is hard to forecast because original data, if we focus on a single data of cn.com or man.com, and they are very noisy and they are very sparse and they're very vast. So it is hard to find a trend. So our goal is to find the hidden topics, business, news, media, and group URLs and group users, and forecast the future events. So, and we can get information of URL in topic space, or user in topic space, or time evolution of topic activities. So, key point of this method is that if we focus on individual sequence, so it is hard to forecast. So it is because it is very noisy. So the point is that we aggregate the data for forecasting to get a trend and for forecasting. So, for example, we aggregate the information of similar users, or like business topic users, or we aggregate the information of similar URL, like cnn.com and cnet.com, business related URLs. If we aggregate such similar information, it is in this case like this. So business topic shows that clear periodicity or typical pattern, or drive so weekly activity is very low, but weekend activity is very high. So we can get the information about the trend. So if we aggregate the information of similar UI or similar users. So yes.
So how are you deciding which topics to use, right? Because not all topics are useful when you do tensor vectorization.
That's right, yes. So yes, so in this case, we automatically estimate the topic. So by using give sampling. So yes, which is useful for example LD or something like that. Yes. So and also in this paper we use a fixed number of topics, but we can estimate the appropriate number of topics by using Embedding. Yes. And yes, so thanks for a good question. So yes, again, so we don't focus on integral sequence. So micro analysis is not good for forecasting. Macro analysis, aggregation is good for forecasting. So in this case, important thing is that we appropriately group the UI and we group the users, which is good for forecasting. And main idea we use memory tensor analysis, and also in this case, this is a tensor, and if we use give sampling, we can decompose such a tensor. Topic number 1 is business, topic number 2 news, topic number 3 is media. So if we focus on business topic, for the URL vector and also user vector and time vector. So if man.com and cn.com are related to business topic, in this case, this element and this element are very high value. And if user Smith and Johnson are interested in business, so their value is also high value. And that's in happen the time vector. So and then we decompose the tensors. And then
we use such a decomposition information for forecast. And we microanalysis is not good for forecasting because problem number one is related to scalability. So time complexity is bad for forecasting. And also, if we focus on single cities, like noise, so 001, 002, 00, it's hard to do the forecasting. So, at first, we decompose the tensor by using give sampling. Then, we aggregate the information of each topic. Then do the forecasting of time vector. And after that, we use future time vector and user information and also URL information, and then create a future event. So, which is the output of this method. Okay, and this is URL topic matrix, but it is for example, car and bike side is related to driving side, or money side and finance side have a similar trend. And the same happens with the user. And also, this is a time topic matrix. Business topic shows a higher activity during weekdays and less activity during weekend. On the other hand, dry topic shows a high activity during weekend, especially for Saturday evening. So this is dry topic issue. And by using such a topic information, we can do forecasting. And next one. Next one. So we introduced a technique of automatic mining and nonlinear modeling and large-scale tensor analysis. We try to put all together. So nonlinear tensor analysis. So we can use it for epidemic data, like large set of molecular data, like middle cases in the United States. And yeah, we can see the yearly periodicity and vaccination effect and shock, external shock like 1 or 2. So yeah, you can download that. This is public data set from type of project or University of Pittsburgh. So this is a tensor with 50 states and also 56 diseases, and time duration exceeds 1 century. And we want to we want to analyze such a data. So given tensor X, we want to find comparative distribution of X with similarity and discontinuity. So for the similarity, this figure, so this circle shows the similarity from the January to December, and also this shows the strength of seasonality. For example, if this is influenza in February identified by our method, which shows strong seasonality. And measles is a children's disease, so which appear in spring. And also tick-borne disease or Lyme disease, which appear in summer. And sexual STD disease, they don't. It doesn't show any periodicity, so it makes sense. So and also we can automatically detect disease reduction effect, and also area sensitivity. So for example, measles, children disease, Pennsylvania and New York, there are more children. That's why Pennsylvania and New York are related to measles. And Florida, it doesn't have any relation because there are fewer children in deployed. And external shock in 1 or 2. And also it automatically captures the mistake or incorrect value or missing values. Because we use a non-linear model. So if it is easier to find a missing value or mistake. So we are running out of time, so let me skip this. Another example is competition, like this. So, given local user activities like Google search volume for Kindle and Nexus, so for 236 countries, so we want to capture the, not only global trend, but also local trend. And also exponential growth, and competition, and seasonality, and delta. So for time sampling events, so we also create a tensor of time and activity means a keyword and location for Google Trends. So in this case, Kindle, yes, Kindle and US and first week of April in 2014. So the data is value is 100. So the problem definition is again. So given tensor X, we want to find complete distribution of X. So with basic, completion, seasonality, and delta. And also we also capture the global local information. So let me give you an example. So we want to find a global local competition for competition of Nexus and Kindle. So Nexus and Kindle are competitive, and because they are ebooks, so and they have competition for global information. But if we focus on local information, so US and Italy had a strong competition for Kindle Nexus. On the other hand, at that time, so Brazil and China, they don't have, in Brazil and in China, they don't have a strong competition. They have a competition, but the competition strength is very weak. So local information is a little bit different. So we analyze not only we analyze to get information about not only global information but also local information. And another example, local seasonality. So if for example local seasonality for iPod, okay? So this is the seasonality. We can see the Christmas light. So yes, so we can get a pattern, seasonal pattern from the tensor, but it is related to Christian countries, like US and Canada, Brazil and European countries and Australia, and also Japan. And another seasonal pattern is Chinese New Year, which is related to China and so on. So we estimate the approved number of seasonal pattern is 2. So which is one is for Christian countries, and another one is China and friendly countries. And another example is news resources. So this figure shows Google search volume for keywords, CNN, Times, BBC News. So this is very typical behavior. So the news resources we can see the big spike. If big news happen or accident happen, so we can see the spike. So let's focus on one spike like this. So which is a spike of US election in 2008, and we have to capture such a spike because this spike is not related to competition, not related to behavior of each news resources. So it is exactly the external shock. So we have to analyze separately, and we capture such a trend automatically, and then we can also use it as another purpose. For example, this external shock is related to several countries. So of course, United States, and also Canada or European countries, Australia. So which means they are US friendly countries. So if this external shock are related to US friendly countries. And so this is a full model of our method, and basic, competition, similarity, and data. And so let me skip the detail. And occasionally it is dense. For example, information with US and information with Carnegie. So sometimes they look similar, so which means they are redundant. So ideal method should be compact and provide powerful representation. So we compress the data and summarize them and separate the. So we model information. We model the global information and also local information separately. So for accuracy, so fitting accuracy, so by using careful design models, so it shows high accuracy, and also scalability is good, and also if we want to forecast tensor, like time and keyword and countries, so we create a model by using training data and use it for forecasting. So this is experimental result. It's SRE plus. SRE plus is a standard package and widely used in various fields like statistics and physics and so on. So and also T-bar is a state-of-the-art method in statistics. So our method is extremely better than these ones for forecasting accuracy. And like this. Okay. So as a conclusion, so real data often in high dimension in multiple aspects, and also tensor, middle system and tensor provide the elegant theory and algorithm. And we also introduced non-linear tensor analysis, and there are differences. So this is conclusions. So this is roadmap. So part one, we introduced similar search and pattern discovery and summarization. And part two, so we introduced a non-linear modeling and forecasting. And part three, we extend the time. We introduce the extension of time series data, right? Which is tensor analysis. So part one, we introduce a similarity search algorithm, and also some fundamental concept and function like Euclidean distance and time distance, and future extraction and spatial access method. And future extraction, we do the Fourier transform and wavelet, and SVD, and independent component analysis, and linear modeling. So we do the odd regression, and RSS for stream, and stream mining. We introduce the start tree and braid. So for to analyze the stream in real time, and we also introduce the automatic mining. Typical approach is MDM. And nonlinear mode forecasting. So black force is one solution, especially log plot plus k-measurement research, which is a very simple solution. And also, if we know the equation or domain knowledge, we can use the gray box model. So different equation. The example of different equation is logistic function or Locked-Portilla equation in biological field. And also academics, SIR or SIR model, and power profile. And we introduce extension of tensor analysis, which is combination of nonlinear modeling and tensor analysis. And also we can also use Gibbs sampling for tensor analysis. Okay, so that's all. So thank you for your attending. So do you have any question? Which is